Okay, so a rough outline for today's class will be, we'll start off by sort of layering on more and more complexity. We'll start off with a basic idea, which is a Markov process or a Markov chain, for those of you who might come across this before. And then we'll start to introduce some of the perhaps less familiar ideas which are central to reinforcement learning. First of all, by adding rewards in to give a Markov reward process, then by adding actions in to give a Markov decision process, and finally we probably won't have time to actually talk about them, but they're in the lecture notes for those of you who are interested. There's a lot of extensions to MDPs where we can move beyond these three settings and add in even more complexity like partial observability and so forth. So I'll begin with the basics. I'll try not to kill myself today on any stage. So the basic idea then is we're going to develop this formalism, the Markov decision process. And what we're trying to cover here is, if you remember in the last class, we talked about agents and environments. We have an agent, that's our algorithm, and that's the brain that we're trying to build, and it's interacting with some world. This might be the real world for a robot, it might be the trading environment for a trading agent, the factory floor for a factory, or whatever. And this environment, we want some description of that environment such that we can understand it, start to apply some tools to it, and really understand what it means to do reinforcement learning in that setting. And that's going to be the MDP. And in this case, what we're going to start with is the nice case, where the environment is fully observable. So we're told the state. So this is the case where we see everything that there is to know about that environment. All the relevant information is presented to our agent. Nothing is hidden away. And one way to think of this is that the current state that's given to the agent, it sort of completely characterizes this process. So the way in which the environment unfolds depends on some state, and we're told that state. We know that state. It's fully observed. And the nice thing about this formalism is that really almost all reinforcement learning problems can be formalized in some way as a Markov decision process. So if we think about even some of these less familiar cases, for those of you who come across them, these are things which people might not first of all think of as Markov decision processes, but the problem of optimal control, where you've got, say, some differential dynamics describing some fluid, and you want to find the optimal way to make your octopus swim through this fluid. How do we actually deal with that? Well, there's an extension to MDPs that's actually a continuous Markov decision process with continuous actions. And optimal control actually really deals with that case. Again, partially observable problems, not only can we think of MDPs to give us some intuition into them, but actually any partially observed problem can be completely converted into an MDP. So it's not the case that these things fall outside of the framework of MDPs. They are MDPs. They really are MDPs. And if you understand the basics, you can solve all of these problems in principle. Some of the simplest cases, which we'll deal with in a later class when we talk about the exploration-exploitation dilemma in reinforcement learning, are what's known as bandits. This is a very common formalism that's used a lot at the moment, where you get just a set of actions, you get to take an action, you get some reward for that action, and that's the end of your task. So this is like the task we talked about last week, where you present an advert to the user on the internet, and that advert either gets clicked on or it doesn't, and you want to be clicked on as much as possible. And actually, this is just a Markov decision process with only one state. So again, it's a special case of MDPs. If we can solve MDPs, we can solve all of these different cases. So it's really fundamental. So what's the central idea to an MDP? Well, we've already seen this in the last class, but it's such an important concept, I'm just going to flash up this slide again, which is the Markov property. And again, the Markov property, the central idea which we're trying to understand here is this idea that you have some state, this random variable S. This is characterizing where we are in our environment. And if it has the Markov property, then this basically tells us that the future is independent of the past given the present. In other words, what happens next in our environment depends only on our previous state and not on all the things which came before that. Okay, so the state completely characterizes everything which we need to know. It captures all the relevant information from the history. And once you know this thing, you can essentially, if you have ST, what this tells us is you can throw away everything which came before. So the set of Markov processes, or the set of states that have this property, it's the set of environments in which everything which we know about the system can be described by this single state at the current time, and we don't need to retain everything that we've ever seen. Okay. So one way to understand this is that for any problem with the Markov property, for any Markov process, if you start in some state S and you've got some successor state S prime, then you can actually define the probability that you'll transition from one of those states to the next state. So remember that this state which we were in characterizes everything about what will happen next. So that must mean that there's some well-defined transition probability that tells me that if I was in this state before, there's some probability, given that I was in that state, that I will transition to some next state. There's some probability that, if my robot is here and I give it a little push, then it will, fall over to here or maybe put a foot forward. All of these things are completely characterized by the state it was in before. Okay? And so this gives us our state transition probabilities. So it's the probability that if I'm in S, I transition to S prime, and that gives us the probability that this random next state will be this particular instantiation of the state S prime, given that the previous state we were in, our current state at time t, was this S. Now, once we have this idea of the transition probability matrix, we can form this into a complete matrix that tells us, essentially, each row of this matrix tells us what would happen for each state that I was in. So if I start in state 1, this tells me the probability that I'll end up in state 1 here, state 2 here, state 3 here, all the way up to n states here. So each row of this completely characterizes the transitions from one possible starting place in this Markov process. So this single matrix now gives me the complete structure to this Markov problem. It tells me from any state, how likely am I to end up in any other state. And so you can imagine now that we can follow this through multiple steps and keep sampling from this transition probabilities, and that will give us some draws from this Markov process. So let's try and understand that a little bit more. So now just formally, a Markov process is basically a random process, a process that we're sort of sampling from iteratively. So that basically, our definition for this is going to be it's a sequence of random states. So a sequence of random states, S1, S2, going on in time, that has the Markov property. That's the definition of a Markov process. It's just a sequence of states with a Markov property. And so all it requires to define this thing is a state space, S, this is the set of states which we can be in, and our transition probabilities that characterize how we transition from one state to the next. Okay? And now this fully defines the dynamics of this whole system. There's some evolution of our robot through this system, or of our trading agent through its environment, or of our chess-playing agent through the rules of the game. All of these things can be defined. No actions yet, no rewards yet, but the dynamics can be fully defined by a state space and a transition probability matrix. Okay, that's the Markov process. So I think it always helps to make these things concrete. So let's try and make this concrete for you guys. So this is my cartoon illustration of what I imagine it's like to be sitting in my lectures. And so we're just going to imagine there's only 3 classes you have to sit through. If you get through all 3 classes, then da-da, you managed to pass the class. If only it was that easy, but anyway. But the problem is that there's all these distractions along the way. So you start off in the first class, and there's a 50% probability you'll make it through to the next class. There's also a 50% probability that you guys will open up your laptops, start looking at Facebook. Now, if you look at Facebook, we all know that once you're in Facebook, it's a little bit addictive. So there's probably about a 0.9 probability that you'll just kind of self-transition and keep looking at Facebook again, and then maybe after you iterate around this thing for a few times, there's a 0.1 probability that you'll actually drop out of this Facebook and get back to the class and listen to the rest of the class, at which point you might make it to the second class. Unfortunately, maybe we're talking about something really tedious like Markov processes, and then you feel a bit sleepy, and so there's maybe a 20% probability you fall asleep, but there's maybe an 80% probability you make it through to the final class, at which point maybe you think, yeah, I'm doing really well, and you get a bit excited and go off to the pub, which means if you go to the pub, you drink a few beers, you might end up either regressing back to class 1 or class 2 because of all the things you forget, or if you don't go to the pub, there's a 60% chance that you'll pass, and then after that you can go to sleep and everyone's happy. Okay, and this sleep state represents a terminal state to the Markov process. A terminal state doesn't need any special machinery. You can think of this as just a self-loop, an absorbing terminal state. It just keeps looping round and round and round. That's what this square represents. By the way, there's a few more seats over here, I think, if anyone wants to just move around. If you're okay, that's fine. Okay, so now that we've got this student Markov chain, let's think about what it means to take samples of this. So what's a sample? A sample is a sequence. It's a sequence of states where we start, for example, in our class 1, and now we're just going to take samples through this system. For example, one sample might look like this, where we go class 1, class 2, class 3, pass, fall asleep. Okay, that's the nice sample. But you might also have another sample that's like class 1, Facebook, Facebook again, back to class 1, back to class 2, and then fall asleep. You might have more complicated samples. Some of them might go on and on for quite a long time. These are variable length. Each of these you could think of as a random sequence that's sampled from these dynamics. Okay, so that's what it means to have a random process, is that you get some random sequence that's drawn from a probability distribution over sequences of states. And the fact that it has the Markov property means that it can be described by one of these diagrams, if you like. It can be described by saying from any state there's some probability of transitioning to any other state. Is that clear? Good. Okay. And now we can look at the transition matrix for this problem. So the transition matrix is fully described now over here. The transition matrix basically tells us for any one of these states which we might have been in, what's the probability of transitioning to any other one of these states. So for example, if we consider class 2 here, and we look across this row here, this row of the transition matrix basically tells us there's a 0.8 probability and 80% chance of transitioning to class 3. But if we go across, there's also a 20% chance of transitioning to the sleep state. And if we look at all of the rows together, that fully describes the entire dynamics of the system. And once we have this matrix, we're able to sample repeatedly from this matrix and get our samples of these sequence of states after this Markov process. Okay. Question?
So these things will only work if the probability is going to stay constant in each state. How do you make it such that if you were to, say, go to Facebook, then you have a reducing probability each time you...
Okay. So the question is, how do we deal with modifications to these probabilities over time? So there's two answers to that. One answer is that you can have a non-stationary Markov process. Later we'll have MDP, so non-stationary MDP. In that case, what you can do is use the same kind of algorithms we use for the stationary case, but incrementally adjust your solution algorithm to just kind of track the best solution you found so far. The other answer is to say, well, the fact that you've got non-stationary dynamics just makes it a more complicated Markov process. That there's some, so you're imagining that there's probabilities that depend on how long you've been in this state and so forth. So now you can augment this state. You can have a more complicated Markov process that has like a counter that tells you how long you've been in this Facebook state. And now you've basically got lots of different states depending on whether you've been in Facebook once or twice or 3 times. And you can have an infinite set of these. You can have a continuous set of these. All of these things are possible, but they don't change the fundamental structure from this being a Markov process.
Cool.
And this is just a particular simple instantiation where we can see everything on one page. But don't let that mislead you into thinking that Markov processes are necessarily small or simple. We can solve very, very complex Markov processes. In the rest of the course, we'll see how to solve MDPs. Some of them have 10 to the 170 states will be one of the examples we'll do later. So these could be very large and complex beasts with a lot of structure to them. Okay, so far we haven't really talked about reinforcement learning at all. There's no rewards, there's no action. So let's start to put in some of that machinery now. And the first and perhaps most important step is to add rewards. And so one way to think of this is we're now going to create what's called a Markov reward process, which you could think of as like a Markov process with value judgments. So there's some value judgment saying how good it is to be in some particular, there's some value judgment saying how much reward will I have accumulated across some particular sequence that we sample from this Markov process. So all we're going to do to add into our Markov process is we're going to add in 2 things. So we had our state space S and our transition dynamics P. Now what we're going to add in is some reward, a reward function R and a discount factor gamma. And let's just talk about what those are and make sure we understand them. So the reward function, first of all, this is something which tells us if we start in any state S, if we're in some state, how much reward do we get from that state only? This is just the immediate reward. How much reward do I get from that state at that moment? And what we care about is maximizing the accumulated sum of these rewards. That's what we care about in reinforcement learning. So for the Markov reward process, we're going to start summing these things together over time. But R, for now, it just tells us for one step. At that moment, if we're at time t in state S, at time t plus 1, we will get this reward. It just tells us what will happen next. Okay. So if we go back to our student Markov reward process, what we're going to do is we're just going to add in some value judgments now. And I'm just going to tell you that, maybe you don't enjoy sitting in the class, so let's call that -2 for each class. -2 reward here, -2. But if you pass at the end of the class, you get this big juicy bonus of +10. Okay. Facebook, maybe you get like -1 per step as your brain gets drained of any sanity that you used to have before you went onto Facebook. And going to the pub, maybe the beer tastes good and you get +1. Okay, these are obviously subjective value judgments we're arbitrarily throwing into this. And then what we care about is the total rewards that we're going to get across a whole chain here. We don't just care about how much reward you get for being in one class. We care about the fact that, maybe you get -2 here, but if you follow through an entire sequence, you might get -2 plus -2 plus -2 plus 10. And that's your overall reward that you get for that sequence, that sample of the Markov reward process. And so what we talk about is this quantity called the return. So we call it the return G. That's kind of, you can think of as the goal. The goal of reinforcement learning is to maximize the return. So G sort of stands for goal here. And the goal here, the return, is the reward summed over all of the time steps infinitely into the future. And the way that we control this return and make it finite is by using a discount factor. So we basically say we're going to discount by a factor of gamma at each time step going into the future. So we're going to get a reward, an immediate reward of rt plus 1 here, but then we're going to get gamma, say, 0.9 times the reward at time step t plus 2, plus gamma squared, 0.9 squared times the reward at t plus 3, and so on, all the way to infinity. Okay, and that's going to be our goal. Our goal is to maximize the sum of all of these rewards. Yeah, question?
Why is there no expectation here?
There's no expectation here. That's a good question. Why is there no expectation here? There's no expectation here because we're just talking about a random sample at the moment. So G is random. G is just one sample from our Markov reward process of the rewards that we get going through that sequence. Later, in a couple of slides, we'll introduce the expectation, which is what we actually care about. So this discount factor then has to be something between 0 and 1. And it tells us, if you like, the present value of future rewards. It tells you how much I care now about rewards I'll get in the future. So it kind of tells me that if I'm at time step 10, and I know I'm going to get a reward at time step 20, then I should discount that an additional 10 times. It's 10 time steps into the future, so we're going to discount 10 more times. So this thing has to be between 0 and 1, and 0 kind of means maximally short-sighted. Like if you have a discount factor of 0, you basically zero out anything beyond your current time step, and you only look at that first reward. And if you have a discount factor of 1, that's maximally far-sighted, where you care about all rewards going infinitely far into the future, and you just assume that your Markov process has the property that eventually these things will all be finite, that you'll get 0, like in our absorbing terminal state, you just get 0, 0, 0 at the end. Okay, so specifically the value of receiving reward R, k plus 1 time steps later, is gamma to the kr. We'll just keep discounting again and again.
Does the discount factor apply outside of problems with, like, financial problems?
Okay, well, I'm going to have a slide on this. So.
Okay.
So really, why should we do this? It's basically, we're somehow introducing a judgment here, which is that we prefer short-term reward to delayed reward. We prefer reward now to reward later. And the amount that we prefer reward now to reward later is given by gamma. So the closer it is to 0, the more we prefer reward now, and the closer it is to 1, the more indifferent we are to when those rewards arrive. So why should that be? That was essentially the question. Why should we do that? So I'm going to turn that over to the audience. So in most of reinforcement learning, we use a discount factor. So I just want to ask you guys, well, why? Why should we do this? Anyone think of reasons?
There's more uncertainty in the future.
Okay, great. So someone said there's more uncertainty into the future. I think that's a really great answer, actually. So one reason to use a discount factor is to basically represent the fact that we do not have a perfect model. So if you imagine that we're just building a Markov process to model the environment, we're building this Markov reward process, but we don't have a perfect model of the environment. So we think we've come up with some great plan. We think we know exactly how much reward we're going to get into the future. But if we don't entirely trust our decisions that we make, if we don't entirely trust our evaluations, we might choose to discount because we might say, okay, well, maybe I can take this pot of gold now, or maybe I should really trust my plan and my model that's going to tell me that all these things are going to happen over the next 10 years, and then I'll get an even bigger pot of gold. Well, you have to really trust your model to wait all those time steps and really believe that things are going to turn out just as you planned in order to get that bigger pot of gold later. So uncertainty, I think, is really one of the major kind of intuitive reasons to discount. Any other points? Any other ideas? Yeah.
When we're trying to plan for the future, if we're very far-sighted, so if we let that sum go to infinity, potentially the rewards can get unbounded. So we would like to pick a sequence where we're going to know that there's going to be some bounded stuff, so we can compare different models.
Okay, absolutely. So to keep the maths bounded, I mean, and actually, so I'll do my first couple of slides here. So I mean, the first reason, it's just mathematically convenient. And I think, honestly, that's the main reason we do it in the MDP framework for RL. Most of the time, it's just because the maths all works out. It's easy to teach. It's easy to understand. And it avoids these infinite returns. So if you have some cycle in your Markov process, and you just get rewards again and again and again and again, you need some mechanism to avoid infinity as your evaluation. Otherwise, the maths just doesn't work out. And there are other mechanisms for dealing with that, which we'll mention briefly. We have the uncertainty. And I just wanted to add in a couple of other ideas. So someone mentioned already the idea that in financial settings it's rather natural. So that's a quite specific setting, but in a financial setting we have this idea of interest rate, that you kind of know that money now is worth more than money later, and that's usually built into the definition of what it means to kind of make financial decisions or trading in a trading system or whatever. So that's a specific case where there's really a meaning to this, that you can think of gamma as like the inverse of the interest rate. But one more point I just want to make is that actually, animals and humans, they actually show a preference for immediate reward. So people have done tests on humans, and it turns out that humans have not quite an exponential discounting, but they have something like a hyperbolic discounting. But certainly animals and humans do prefer to get reward now than reward later. And so you can think of this as a cognitive model as well, of how biological decision-making operates. And finally, I just wanted to mention that if you don't agree with these points, which I think is perfectly legitimate, to say, well, hey, look, the problem I care about really is artificial to introduce a discount factor. I'm only doing it to make it convenient. There are alternatives, and there's undiscounted Markov reward processes. The simplest case being where we know that all sequences terminate. So if we go back to our student MRP, we know that all sequences ended up with, at some point, falling asleep, one way or another. And so if we know that's the case, then all sequences end, or at least end in this absorbing terminal state, which keeps getting 0 and 0 and 0 again. And therefore, by definition, all returns are finite. And so then it's fine. There's also a formulation that's in the extended notes for this class, which is the average reward formulation. And there it's possible, even with infinite sequences, to still deal with the undiscounted sort of evaluation of Markov processes, Markov reward processes, and MDPs.
But just to clarify, not all sequences terminate in the example you gave before. There are infinite sequences that would not end up in the sleep state.
No, that's not true. So any single sample which you draw from this Markov process, by definition, is finite, of finite length.
You mean there isn't some part of that process where I could just end up in an infinite loop?
So any sample which you draw, it's impossible to draw a sample that's infinite. Like, by definition, the sample that you draw will terminate at some point. That's the definition of this process. And so even though the decision process itself contains infinite loops, any single sample that you draw will be a finite length and will terminate. And the only question is at what step it will terminate. Okay. Right, so now someone asked about expectations. And so this brings us to the value function, which is really the central quantity which we're interested in RL. So the value function, this is the quantity we really care about. It's the long-term value of being in a state. So if you're in this state S, so if you're in some concrete state S, how much value will you get from there on? What's the total reward that you'll get from that state onwards? So formally, it's just the expected return if you start in that state. So if I drop you into this Markov reward process in some state, like if I drop you in class 2, how much reward will you get from class 2 to the end until you terminate? That's basically what it's saying. How much reward will you get from then onwards? And we have this expectation because the environment is stochastic. We were in this stochastic Markov process. The evolution of states might go one way one episode and another way the next episode. What we care about is the expected return over all of those different episodes. And that's the value. That's how good it is to be in any given state. So this is the central quantity. We prefer states. We prefer to be in states that give us more total reward. And so the formulation of our problem is to say, let's first of all just measure that. So in an MRP, there's no concept of maximizing. We're just saying, let's just measure how much reward we'll get. But when we get to MDPs, we want to maximize this quantity. Okay, so let's get concrete again. Let's go back to the student Markov chain, actually the student Markov reward process. So we're going to sample returns now. So again, we're going to look at these samples of this process that we've taken. And we're going to consider a discount factor of gamma equals 0.5. So we're basically halve the amount that we care about getting rewards at every step. And so this is the definition of our return, with gamma instantiated with a half. And so now if we just look at the value of these guys, so these are basically like the returns here. So you get -2 at the first step, -2 discounted by a half, -2 discounted by a quarter, and then at the end of it you got this +10 reward for finishing the class, all 3 classes, and that's discounted by an 8. You sum those all together, you get -2.25. So that's one sample of the return. So this guy should say G1. And now we've got 4 different samples here. These are different samples of the first 4 different sample sequences through this Markov reward process. So what's the value of being in this state? What's the value of the start state? Well, one way to estimate it is you can just take a bunch of samples and just take the average of these values, and that would give you a legitimate estimator for the value function, the value of that state. So the returns are samples, they're random, but the value function is not a random quantity. It's an expectation over these random variables. Okay, is that clear?
So why are we starting G1 indicates that we start from state 1, say class 1?
No, this is these subscripts are time steps. Okay. So G1 is, so here we're basically saying, so the definition, if we go back to the definition of return, the definition of return was the return starting at time step t is the rewards from that time step onwards. Okay, so now we're considering a bunch of different returns. We are also starting from S1 equals C1 in this case, but this thing's actually, the subscripts are time steps.
And they're observed. The point is here, there's no expectations because we're essentially saying that we've observed these sequences.
These are observed samples of our random process, and if we want to ask about the value function to make an expectation, we're asking what's the expected return, what's the expected number that's going to pop out of this at the end. What's the average of these numbers, and that's how good it is to be in this the first state of this student Markov chain. Okay, so what does this look like? So let's consider a couple of different discount factors. So first of all, this is the maximally short-sighted view of the value function. So this is the value function now for gamma equals 0. This is where we literally don't care about anything except one step of immediate reward. So if we take any given state here, so now if we consider class 2 state here, we know that no matter what we do afterwards, we're going to get a reward of -2 at this time step. It doesn't matter that we're going to get these other things and this +10 later. That's irrelevant because we're just looking at how much reward we get at this time step onwards. So the value of being in this state is -2. That's what we're going to get. We're going to get -2 whether we go to sleep or whether we go this way, we're going to get -2. That's just the definition of it. However, if we look at a more long-sighted discount factor, so this is like 0.9 now, then the values all change. And now we have to consider, well, if I was in this state, I'm going to get a reward of -2 now. But then, with 0.8 probability, I'm going to transition over here into a situation where I'm going to get additional rewards, -2, and then probably +10 again, and so forth. And when we factor that all together and compute it, and we'll see how to compute these things later as we go on, the value of this state actually becomes much better. We can get 0.9 reward from this state onwards, kind of averaging over the probability of falling asleep and continuing through the classes. So that's the value. That's the average now. The expectation over all of the different paths that we can take through this system, taking an average of them, that's the number that kind of summarizes how good it is to be in that state. We're going to get 0.9 units of reward from then onwards if we start there. If I drop you into that class, 0.9. That's how good you are. Okay? So now we're going to talk about, this is maybe the most fundamental relationship in reinforcement learning. You might have come across this in dynamic programming. It's very widely used. And it's called the Bellman equation. And the idea is that the value function sort of obeys this recursive decomposition. And the main idea is very simple. That it basically says that you can take your sequence of rewards from this time step all the way onwards, and you can break it up into two parts, which basically consist of the immediate reward that you're going to get, and then the value that you'll get from that time step onwards. So you break it up into immediate reward, and then from the successor state that you end up in, the value of where you end up. So immediate reward plus the value of where you end up. You know, if I'm a robot, I might get an immediate reward of like plus 10. But then I end up in this new state, and the question is, how good is it to be in this new state? And so the overall value function of being here is like my 10 points of immediate reward plus the value of where I ended up. And that's what the Bellman equation tells me. So formally, if we just step through this, it's very straightforward. So this is our value function. The value function is the expected return, given that I start in a particular state. So that's how we want to know how good is it to be in this state, and it's the expected return if you start in that state. If we just unwrap the definition of return, the return is just the sum of these rewards going into the future, discounted. We can break down those sum of rewards into the immediate reward plus the discounted value, the discounted return from the next step. So we've got we just pull out the discount factor. We've got starting from RT plus 2 plus gamma RT plus 3 and so forth. Just pull the factor of gamma out. And now we see that this thing here is just the return from the next time step. The return starting from t plus 2 instead of from t plus 1. So that's this thing here. We'd say it's the expected immediate reward plus discounted return. And then, by the law of iterated expectations, what we can do is basically say the expectation of this return is the same as the expectation of this return. That's called the law of iterated expectations, which gives us this final line here, which tells us that the value function in state S is equal to the expected immediate reward plus the value function at the next state. Yeah, question?
I'm slightly confused with the indexes here. Like, when we start in state st, but the time is t, and count the reward, the first reward at like t plus 1.
Okay, so the question is, why do we index the reward at time t plus 1? Actually, you'll find both in the literature. So we're following the Sutton and Bartow convention, which indexes rewards at time step t plus 1 rather than time step t. This comes from how we think of the boundary between agent and environment, that the idea is that the action that we take goes into the environment, then a time step happens whilst, that we switch our time index after control passes back from the environment to the agent. We're in a new time step. So at that point, everything we receive from the environment has a new time index. So everything after the environment is a time step t plus 1. You might even find that my slides might be slightly inconsistent on this point, so it's a good spot. So I'm sorry if that's the case. Yeah.
Actually, if we define it that way, when gamma is equals 0, the actual values of the state won't be the immediate rewards, but will be the probability of like if you go to the slide where gamma is equals 0, the actual values of the states are going to be different because they are, I think.
No, that's not true. It's just a difference. It's literally just re-indexing. So you can re-index everything with RT instead of RT plus 1. It's not going to change any of the math and any of the semantics. It's all the same. So,
in the previous slide, the reward with zero discounting was the reward in the state that I'm currently in. If you set gamma to 0 here, it looks like the reward for the state I'm currently in is the expected reward of the next state. Which I think is exactly what.
It just depends. No, it just depends on how we define RT. Like, where does that time step t refer to? So here, what we're saying is this is actually, if we move into this state at time step t, then this figure now indicates that this reward is what happens at time step t plus 1. That's all. That we move into this state, and then we get this reward no matter what we do.
The indexing of the rewards and the states is sort of.
So it's just a convention. It's just a convention. So don't confuse yourselves. It's just a convention. Stick to the very intuitive idea that you move into a state, you get some reward, everything is good. Okay. Okay. So let's just try and understand this Bellman equation a little bit more. So the Bellman equation. So this is our Bellman equation. The value function now is equal to the expected immediate reward plus discounted value at the next state. So value now, take a step, see what the value is in the state I end up. And that's just like a tautological definition. If we've got our value function correct, it must obey this identity. That's what it means to have a value function. Okay, if we don't obey this identity, we haven't found the value function yet. So one way to understand this is by using what we call these backup diagrams here. So these backup diagrams, this is basically showing us, you can think of this as like a one-step look-ahead search. So we start in this state S, and we can look ahead one step, if you like. So this state S leads to a value function of V of S. If we go down to S prime here or here, we're going to have a value function that's V of the successor state. Okay, and we're going to get some immediate reward along the way. So this diagram is just kind of showing us that we can think of this as a one-step look-ahead tree. where you start in this state, you look ahead one step, you integrate over the probability of each of these function here. Okay, so it's a one-step look ahead with like this averaging, where we kind of go ahead one step, we average all the possible outcomes together, and that gives us the value function at this step. And that's actually kind of the way that we're going to proceed when we actually start to build algorithms. They're going to do something like this look-ahead process, which is why it's useful to have these backup diagrams in mind. Okay, so if we think about the value function now, let's just pick out one state. So if we pick out this state here, so this is the class 3 state. And so I'm just going to tell you that this is going back, I think this is a discount factor of 1 now, so it's undiscounted. And what we're looking at is what happens if we're in this state with no discounting. So I claimed that this was the value function of this MDP, but how can we verify that? Well, we can use the Bellman equation to verify that. We can say, okay, well, if this value function is 4.3, it should really be equal to doing like a one-step look ahead, averaging over all the things which might happen next, and then ending up back here again. Okay, so let's see if that's really true. Well, from here, there are two things which could happen. So we could either basically get, so we're going to get -2 immediate reward no matter what happens. Okay, that's this -2 here. And then with 0.6 probability, you're going to move through to the next class and end up somewhere with a value of 10. But there's also 0.4 probability that you'll go to the pub and you'll end up in this state which had a value of 0.8. Okay, so if we sum those things together, we get -2 plus 0.6 times 10 plus 0.4 times 0.8, which to numerical precision is 4.3. Okay, and so that sort of validated the fact that this really is the value of this MDP.
I'm not very clear. What is this capital R represents? Is it a reward for doing a step?
This is
no matter where.
okay. So I think I need to be clear about the rewards. I think a few people are. So let me try and explain that more clearly. What this diagram represents is that you're in some state. When you exit that state, regardless of what you do, you will get the reward indicated by this R. Okay? So upon exiting that state, regardless of where you end up, you will get this -2. So we could have duplicated this and written R -2 here, R -2 here, and it could have been on these arcs. And actually, when you define Markov reward decision processes, which we'll see later, and for Markov reward processes, you can make it dependent on the particular arc that you take. You can make it dependent on the action. You can make it dependent on the successor state. All of these things are possible. This is the simplest formulation. The rewards just depend on the state that you're in, and that state determines how much immediate reward you'll get. And then you have to look at where you ended up to see how much immediate reward you'll get on the next step. So you start here, you exit it, you get -2. You get to here, you exit this state, you get -2. You exit this state, you get -2. You exit this state, you get R equals 0. Okay. Sorry, you get +10. You exit this state repeatedly, you get 0, 0, 0, 0. Yeah, last question, then I'll move on.
I guess that's the reason why one needs to exit the past state to get the reward of +10 to go to sleep.
Yes.
That's why.
Yes, thank you. Okay, let's move on. Okay, so this Bellman equation, so far we've seen how to kind of spell this out literally state by state, but there's a much more concise formulation which is using matrices and vectors. So if we just spend a moment to understand that, what we can do is basically use this matrix formulation of the transition matrix, which we've already seen. But now what we're going to do is we're going to introduce a vector representation of the value function, which is the obvious thing. It's basically we form a column vector where each element of the column vector contains the value function of a specific state for all states from 1 to n. Okay? And so now we can write out our Bellman equation very concisely. It's just that the value function that you start with, this column vector here, is equal to, and we're going to do the same thing with the reward function as well. We're going to write out the reward function with one element per state. This tells us how much reward you'll get from exiting state 1, all the way down to how much reward you'll get from exiting state n, so forth. Okay, so this is your immediate reward, and then this is how much, this is where you'll transition to, and this is how much value you started with before. Okay, so it's basically telling us that in one sweep, we can just look at this thing. We can say the value of this state is equal to the immediate reward plus the transition matrix. So these are all the places we might transition to, and then this is the value of where we end up. Okay, this is the value of, after I've taken a step, I might end up in this state, I might end up in this state, I might end up in this state. And each row of this thing is going to be dot producted with these values. So there's some probability if I'm in this state that I end up in each of these successor states, and then we take the dot product of that with all of the values of where we end up, and that's going to give us this first entry here. So it gives us, literally, it's a way of writing out the entire Bellman equation in one very concise form. Okay, yeah, question?
Transition matrix, should that be N1?
Yes, that should be Pn1, thank you, in the bottom left. Okay, so the Bellman equation is a linear equation. As a result, it can be solved directly. It's one of the nice things about linear equations. This is not going to be true once we move to the more complex case with Markov decision processes. It's a nice property of just evaluating the rewards, but once we want to maximize rewards, it gets harder. But at this stage, at least, we can solve this directly. Assuming that our matrix is small enough to invert, what we can do is just write out our linear equation now. All we're going to do is collect together the v terms here. So we've got, if you like, identity times v here, and gamma p times v here. So we collect those together on this side, I minus gamma p, v equals r, and then we just invert this matrix. Okay? And this is the solution to the MDP. The computational complexity of inverting this matrix is n cubed for n states. So this is not typically a practical solution method for large Markov processes. So what we'll start to look at in subsequent lectures is efficient ways to solve these problems. In particular, this is just going to be a building block. All of the things we've seen so far are just building blocks towards what we really care about, which is making decisions. And so this is just going to be a building block. We need to be able to efficiently figure out what's the value of being in this state. We can't always do this. But it is nice to know that for small Markov reward processes, we can just invert this thing, and it gives us some intuition into what's going on. So later we'll talk about, next lecture, in fact, next class is dynamic programming. That's a very well-known class of methods for basically doing this more efficiently. Then we'll talk about Monte Carlo evaluation and temporal difference learning. That's like, the next couple of lectures are basically doing exactly that. Right. So that was sort of the elementary building blocks leading up to this point, which is the MDP. This is the thing which we actually use in reinforcement learning. And so I guess I should pause. Any questions so far? I guess we've been doing them as we go, so. Right. So the MDP, we're basically going to add in one more piece of complexity now, which is actions. So far there's been nothing for us to do. I just told you get plonked down in your student Markov reward process, and you just randomly sample these transitions and get spat out at the other end. You didn't get any. You didn't have any agency. You weren't able to take actions and make decisions. So let's now change that. Let's introduce decisions. So what we're going to do now is basically take our Markov reward process, which was a state space, transition matrix, reward function, and discount factor. We're going to add in one more component, which is the action space. So A is now a finite set of actions. In the extensions to the class, you'll see how this can be made continuous or infinite. But for now, we'll consider the simplest case. This is a discrete set of actions, finite size. And so now what we're going to do is say the transition probability matrix now depends on which action we take. So where you end up is now going to depend on the action that you take. If you move to the left, the probability that you end up in all these different states is going to be different to if you choose to move to the right. The wind might blow you different ways in each case, but you have some agency over where you're going to end up. So the way we think of this is that there's just one, in the discrete case, there's like one separate matrix of transition probabilities for each action that you might take. And now we've got this reward function. The reward function, again, may depend on the action. May also not depend on the action. But in general, this thing can depend on the action. Apart from that, everything is the same. The machinery is the same. We've just introduced actions in the simplest possible way. So what we're going to do is actually redo our student Markov process now, but as an MDP, where there's decisions that you can take. So the decisions are now these red labels on the arcs. And so the point now is that you actually have some agency here. And so from this state, you can choose to either study. That's a choice now. So there's no probabilities attached to this. You can choose to study. If you study, you end up in this state. If you choose to go on Facebook, you end up in this state. When you're on Facebook, you can choose to do it again, or you can choose to quit. You can choose to go to sleep here or to study again. You can choose to study again, or you can choose to go to the pub. If you choose to go to the pub, that's the only place now that there's any randomness. If you choose to go to the pub, who knows what might happen? You know, maybe you'll drink 1 or 2 beers, not quite sure. So now there's some probability that you'll end up going back to class 1, going back to class 2, or even going back to class 3. Okay? So there's a lot more control that you can exert now over your path through this MDP. This is the reality for an agent. And the goal is, the game we're playing now, is to try and find the best path through your decision-making process that maximizes the sum of rewards that you get. That's the game that you play in an MDP. Okay. So to do that, the first thing we need to talk about is formalizing what it means to make decisions and to take decisions. And to do that, we define something called the policy. So the policy is basically, we can talk about stochastic policies today, and these policies are distributions over actions given states. So in other words, if you're in some state S, this distribution basically gives you the mapping. It says, like, if I'm in this state, map from that state to some probability of going left and some probability of going right. So this is the thing that tells me if I'm in class 1, I am going to choose to go to class 2 with probability 0.9 and to go onto Facebook with probability 0.1. This is something under the agent's control. It's something we decide, and it's just a stochastic transition matrix. And it's useful to make it stochastic because that allows us to do things like exploration. So we'll make use of that later in the course. So once you have a policy, it completely defines how that agent will behave. And in an MDP, the policies depend just on the current state. That was the Markov property. It doesn't depend on the history. And as a result, we consider what we call stationary policies. We don't consider so all of the policies the same no matter what time step we're in the MDP. We just have the same policy at each time step. And the only thing that this depends on is the state that we're in, not the time step at which it happened. And that's sufficient to behave optimally because by definition we have the Markov property and this state S fully characterizes everything that will happen next. Yeah, question?
There is no rewards variable here at all. And then surely if you want to maximize rewards, the shop becomes
The question was, why are there no rewards in this equation? And that's because the state S fully characterizes your future rewards. So in a Markov reward process or Markov decision process, the Markov property means that S fully characterizes the evolution from this state onwards in the process. And so what you're looking for is the policy which, given the state you're in, will you want to pick actions that will get you the most future reward. And so all you need to look at is what state am I in and what action should I take next. And we're trying to pick those actions in the way, given that state, that will get us the most future reward. So the rewards are in the future. We don't care about how many rewards we've got in the past. Those rewards have gone now. They've been consumed. All we care about is how much reward we can get from now into the future. So we don't actually care, when we try to maximize this thing, we don't care if we've already achieved 1 million reward or minus 1 million reward. That's irrelevant. What we want to do is maximize the reward from now onwards. That's the way we're going to behave optimally.
Our definition of state, information-wise, includes all the information about the expected future rewards, right?
Yes. Yes. Exactly. Okay. So one important thing to note about the connection between Markov decision processes and Markov reward processes is that we can always recover an MRP or a Markov process from our decision process. So just to understand that, we can think about basically the sample of states that we draw. Like if we have some policy that helps us pick actions, we're just going to draw this sequence of states. And the sequence of states that we draw when we follow our particular process is actually a Markov chain. It's a Markov process itself. No matter what policy we choose, that policy defines some Markov chain that actually defines our dynamics, the way that we're going to move through and evolve through this system. And if we look at the sequence of states and rewards that we receive as we pass through, like once we fix the policy, if you fix the policy and look just at the sequence of states and rewards that you see as you go through this MDP, that sequence is a Markov reward process. And the way to understand that is that we're going to define basically transition dynamics and a reward function which just average over our policy. So we're just going to average over all the things which happen under our policy. We're going to average over, so we're going to define the transition dynamics to be the average of the transition dynamics for all of the things that we might do. So if we're going to go left with probability 0.5 and right with probability 0.5, I'm just going to take 0.5 times the dynamics, or the probability of going to all the states from here, plus 0.5 times the probability of all the states that I'm going to end up in over here, sum those together, and those average dynamics define some Markov reward process. So we can always flatten our MDP, given our current policy, back into a Markov chain. This is just a useful point. It's not like central, so you can come back to this and think about it offline if you like. Okay, what is central is the concept of the value function. So we already had the value function for a Markov reward process, but there was no agency there was no decisions. Now we've got this policy. There's some way that we can choose to behave in our Markov process. You know, I might be following this path straight through the student Markov chain where I collect all the rewards by going through all the classes, or I might choose to spend a lot of time on Facebook. These are going to give different rewards. There's not one expectation anymore. There are different expectations depending on how I behave. And so we subscript our value function by the policy that we're interested in evaluating. So v pi of s now tells us how good is it to be in state S if I'm following policy pi. So if I'm following the policy that just goes straight through the classes, how much reward will I get? Or if I'm following the policy where I stay on Facebook for as long as possible, how much reward will I get from each state onwards? And so this basically is defined. We've just got this expectation here now. This e pi basically means the expectation when we sample all actions according to this policy pi. That's sort of hidden in that e pi notation. We're also going to define a second type of value function called the action value function. So far we've got the state value function. This v we call the state value function. That tells us how good is it to be in a particular state S. We're also going to define the action value function, which tells us how good is it to take a particular action from a particular state. And this is the thing which we intuitively care about when we want to decide which action should I take. Should I go left or should I go right? Well, I should choose the one that's going to give me more reward. And the way I evaluate these things is by looking at the action values. In other words, we're basically going to look at, so q pi, so for a given policy, for a given way to behave, we want to know if I'm in this state S and I take this action A, what's the expected return, the total reward that I'll get after I've taken that action, how much reward will I get from that point onwards? Okay? That's the key quantity that we're going to use to help us optimize our MDP and pick the best actions. So let's make this concrete again. So this is the state value function for the student MDP, undiscounted, so the discount factor is 1. And this is just for uniform random behavior. So we're fixing the policy to say we're always, when we've got a choice, we're always going to randomly pick 50-50 between those choices. Okay? And so this is the value function that we end up with. We see that we end up thinking it's not very good to start in this state here because there's a high probability of ending up in the Facebook state because we're choosing things 50-50. Now what we can define is another Bellman equation. So the Bellman equation, we saw this in the Markov reward process. Now we're going to define a Bellman equation for these value functions in the MDP case. So again, we can use the same idea, that the value function can be decomposed into an immediate reward plus the discounted value at the next state. So again, there's this idea that wherever you are, you take one step and you get your immediate reward for that step, and then you look at the value of where you end up, and the sum of those things together tells you how good it was to be in your original state. That's still true in an MDP. Now what we're saying is that you start in this state, and we know that we're following policy pi, but the value of being in this state is still the immediate reward that you get, plus the value of your successor state if you know that you're going to follow policy pi from there onwards. So we just look at what happened for one state of, for one step of following a policy, and then we ask how much more reward will I get following that policy. And we sum those things together, that gives us the Bellman equation. We can do the same thing with the action value function, with these Q values. And this basically tells us now, if I'm in one state and I take an action from there, then I'll get some immediate reward for that action, for that specific action. And then I'll look at where I end up, and I can ask, well, what's the action value of the state that I end up in under the action that I would pick from that point onwards? Okay? So let's look at these kind of pictorially and try and understand them with these sort of look-ahead search diagrams. So the way to understand this is, first of all, to understand how V and Q relate to each other. So if you're in a state value function here, really what it's saying is that we're going to average over, basically we're going to average over the actions that we might take. So there's some probability that we'll take this action here. These black dots represent actions and these open circles represent states now. So we're in some state here. We might take this action here. We might take this action here. The probabilities of these things are defined by our policy. So this is like the probability I'll go left, the probability I'll go right. And for each of those actions we might take, there's a Q value. There's an action value telling us how good it is to take that action from that state. And so what we're doing is we're doing like a one-step look ahead, saying the state value, how good it is to be in this state. We just look ahead one step, look at the action values, average them together, and that tells us the value of being in that state at the top there. Now let's do the converse, understand the opposite step. So what happens if we start off taking some action? So now the root of this tree is a state, and we're considering a specific action that we take from that state. So that's this black circle here. So this is like saying, you know, I'm in this particular state here, and I'm asking the question, how good is it to go right from that state? Okay, and how good it is, we now have to average over the dynamics of our MVP. The environment might blow me over here. The environment might blow me over here. So after I've gone right, I might get blown to all these different situations. And we want to ask, for each of these situations I might get blown to, how good is it? What's the value of being in that situation under my current following my policy after that point? We average over all these things using the probabilities of our transition dynamics. We average them together, and that gives us the action value function at the root here. Okay? So V is telling us how good is it to be in a particular state. Q is telling us how good is it to take a particular action from a given state. State value function, action value function. We can put these together now. So this is basically just stitching together the two figures from the last two slides. And now what we'll see is we get like a recursion that helps us understand V in terms of itself. And this is how we end up solving Markov decision processes. So at the root of the tree now, we've got the value function for a particular state. It tells us how good is it to be in this state. And the way we're going to understand that is by doing a two-step look ahead. So we can look ahead, we can consider all the actions we might take next, go left, go right. We can consider all the things that the environment might do to us. It might blow me over, it might keep me standing up. It might blow me over, it might keep me standing up. There are all the things the environment might do. And then for each of those things the environment might do, there's some successor state that we'll end up in. We want to know, well, how good is it to be in that state and carry on with my usual policy? How much reward will I get if I carry on from that point? Now, if we average these things all together, we're basically averaging in two ways now. We're averaging over our policy. We're weighting each of these arcs by the probability that our policy will select left or right. We're averaging each of these arcs by the transition probabilities that will end up getting blown in one direction or another. We average it all together, and that gives us the value of being in the root of this diagram here. It tells us how good is it to be in a particular state. So this is the Bellman equation. You can do exactly the same thing for action values. There's a recursive relationship. You can look at this offline. I don't want to sort of belabor the point. But it's just stitching the diagram together the other way around, and we end up with exactly the same idea, that starting from a particular state in action, we can now look ahead two steps, consider where the wind might blow us first now, and then consider, from the state the wind might blow us to, which action might I take next? I might choose to go left, or I might choose to go right. And now we average over this thing again. We look at the value of that particular action, the Q value, average these things all together, and it tells us something about the Q value of this start action here. So the Q value relates to the Q values at the next step in this slide, and in the previous slide, the state values here relate to the state values at the next step. So you get these two recursive relationships explaining how the value function relates to itself at the next step. But in all of these cases, if you just look beneath the math, it's a very simple idea which says the value function at the current time step is equal to the immediate reward plus the value function of where you end up. That's all these things are saying, just with different ways of putting together the maths. Okay, so let's do that for one example in our student MDP, and then we'll move on a little bit. So here's our student MDP again. We're going to consider just one state, this red state here, so the class 3 state. And again, I'm just going to verify, we're not kind of using this Bellman equation to compute these value functions. We're going to use it to verify that this indeed does have the value of 7.4. Okay? So how can we verify it? Well, we can unroll, we can do our look ahead. And what we're going to do is we're going to do our look ahead for the state value function here. So we're saying the state value function of 7.4 is equal to all the things which we might do from there. So what are the things we might do from there? Well, we might study. Remember, we're doing things 50-50 with for now, with 50% chance we choose to study and 50% chance we go to the pub. So under that policy, where we do everything 50-50, so yeah, this whole diagram is showing us the value function for the policy where we choose all of our decisions 50-50. And under that policy, we start in this state. There's a 0.5 chance we'll take this arc and get plus 10 reward. That's this part here. There's also a 0.5 chance we'll end up taking this arc, end up in the pub, and the pub might take us with 0.2 probability over here, 0.4 probability over here, 0.4 probability over here. And in each of those cases, we'll end up in a different state with a different value. So there's a 0.2 chance we'll end up in this value state here with value minus 1.3. There's a 0.4 chance we'll end up in this state with a value of 2.7. And a 0.4 chance we'll end up in this state here with a value of 7.4 again and end up where we started. So you can see this is quite cyclic, this thing. And so that's this equation here. We just sum those things together. So we're summing together this look ahead of what might happen after one step of taking actions and one step of where we end up. And when you add this together to one decimal place, you get 7.4. So we sort of verified that these numbers are self-consistent for this one state. You can verify them for all of the other states, and you would discover that this Bellman equation does indeed hold, and therefore these numbers do represent the value function for this MDP. So that basically tells us now we really know how good is it to be in each one of these states. You really will get 7.4 units of reward in expectation if you just behave according to this policy. Okay, is that clear? Right. So, that's all very well, but it doesn't tell us the best way to behave. And what we really care about in an MDP is figuring out the best way to behave. Okay, just briefly, before we do that, so I briefly introduced earlier, and I said it wasn't essential, but this idea that you could flatten any MDP back into a Markov reward process by defining these averaged state transition dynamics and averaged reward function. And of course, once we've averaged those things, that gives us a Markov reward process. We know how to solve those things already. So at least one way to solve that, another way to have solved for these numbers would have been to form these matrices, form the matrix of our transition probabilities for all of our actions, average them together to get our p pi, average together our immediate rewards to get our r pi, solve for this equation here, and that would have spat out our actual value function. So that's one way to arrive at the solutions, and we'll look at more efficient ways to do it going into the future. But you should at least understand the idea that the Bellman equation gives us a description of the system that we can solve. And once we solve for this thing, it tells us exactly what the value function is. So one linear equation, we solve it, you've got the value function, you're done. Okay. Right. Now, for the last half an hour, I want to talk about the essential problem we really care about, which is finding the best behavior in the MDP. But I'll just pause for a moment, sorry, I know there's a lot of material, so any questions at this point? People
the slides
tracking?
online are slightly different, just minor changes to these. Are you going to put the newest ones online?
I'll put the newest ones online immediately afterwards, yeah. So it's mostly notation change. I changed the notation to match the new edition of Sutton and Barter.
Can you just explain again what happened to the state pub, which seemed to have turned into some other It used to be a state, right?
Yeah, so when we moved from the Markov reward process to the Markov decision process, we changed the definition of the problem. So pub used to be a state, now it's a decision that we're making. We're taking a decision now. So we're making these decisions of whether to go to a pub or whether to study. So it's actually a different problem that we're studying now.
So pub is an action now.
Here, pub is an action, yeah.
But it ends up at something which isn't a state, whereas study ends up in something which is a state. So what?
No, everything ends up in a state. So if you take the pub action, you end up at this black dot represents like a chance mode.
You mean you can't stay there?
You can't stay there, no. The action takes you to here, and the environment immediately transitions you to here, or to here with these probabilities.
Right.
So you can think of this as basically telling you the dynamics. So if you take this pub action, you're basically going to be teleported to here, here, or here. You'll get a +1 reward along the way, and the probability of ending up here, here, or here is given by these numbers.
But
That's what it means.
Okay. Why did you do that? I don't understand. Why did you now have this separate sort of this sort of transient state?
Because I wanted to illustrate an example where you have some agency, where you have some control over what happens in the environment.
Right.
And now it's a choice whether to go to the pub or not. And the randomness is now what happens after you go to the pub.
So all the other states could be considered to be the same as that, but with just a probability of 1 of going to their
Exactly.
their next
Everything,
state.
you can implicitly imagine there's one of these black dots in every one of these other arcs. So if you go to Facebook, there's a black dot here that says the action is taking you to that black dot, but that black dot is always taking you here with probability 1.
Okay.
And actually now, they say that action also have rewards.
Mhm.
Earlier on, we were saying only that the state has rewards, and now that's actions.
Yeah, if we go back to this was all in the definition of MDP. So if we go back to the definition of MDP, the red highlights here indicate what changed from the Markov reward process. And one of the things which changed was that the reward function was now indexed by both state and action. So the reward does depend on the action you take. That's the definition of an MDP. Okay, so what you do might affect the immediate reward you get as well as the state you end up in. So sometimes there's a cost to the action you take. That's the simplest case. Like imagine a trading agent, you buy £1,000 of goods from someone. That immediately costs you £1,000 compared to the action of do nothing, which costs you 0. So there's a cost associated with the specific actions, and they take you to different states. So that's really the commonest case. So you should intuitively expect that rewards have different effect depending on the particular action you take.
So it's a form of non-determinism, then, really, this sort of possibly taking an action but ending up probabilistically in one of a number of different states.
An MDP is stochastic. The stochastic transitions depend on the action that you take. So you get to take an action, the environment gets to roll the dice and tell you where you end up. So it's a combination of your actions and the dice which get rolled by the environment which determine what happens next. Okay, good. Where were we? Okay, so now let's talk about how to find the best possible solution to the MDP. So what we really want, we don't really care about how much reward we'll get following this crazy 50-50 policy in the student Markov chain. What we care about is finding the best path through the system. In general, you want to find the optimal way to solve your problem. And so let's define what that really means now. And so we're going to start with value functions. We're basically going to say this V star, the optimal state value function, V star, is the maximum value function over all policies. Okay? So what we're saying is there's all kinds of different policies we could follow in our Markov chain, and what we care about is the best of those. We care about understanding what's the maximum possible amount of reward that you can extract from this system. There's all these different ways you can traverse this system. Each of your different policies is going to lead to a different evolution. Stochastic evolution, we care about which of those is going to lead to the most reward in expectation. That's V star tells you not what the best policy was, but what's the maximum possible reward you can extract from the system. Similarly, the optimal action value function, Q star, tells you the maximum amount of reward you can extract starting in state S and taking action A. So given that you actually commit to a particular action, what's the most possible reward you can get from that point onwards? So you start in some state, you know that you're going to take left, but what's the maximal possible reward you can get after you've moved left? And what's really important about this guy here is that if you know Q star, then you're basically done. If you want to know the optimal way to behave in your MDP, what would you do? Well, if someone told you the maximum possible amount of reward you could get over all policies, given every action that you might take. So this is basically telling you, under all different ways you could behave, if you go left, you might get 70 units of reward, but under all different policies, if you go right, you can get 80 units of reward. Well, what do you do? Which way do you go? You go right. You get 80 units of reward rather than 70 units of reward. So this immediately tells you the right action to take. If you have Q star, you're done. You can kind of declare victory. You've got the quantities necessary to behave optimally within your MDP. So we could say it informally that an MDP is solved when we know this optimal value function. So solving an MDP, you can think of as finding Q star. So let's just look at that. What is the optimal value function here? So again, we're going to look at the undiscounted case just to keep the numbers simple. And in this case, it should be fairly intuitive. You can kind of even work this out, just by eyeballing it. That if you're in this state here, should you go to the pub? Should you study? Well, if you study, you're going to get this plus 10 big juicy reward and go to sleep. So that turns out to be the optimal value. We'll see more formally how to derive that in a minute. If we go back up to one state here, we can either go to sleep and get a reward of 0 along the way, or we can study and end up in this nice juicy state with a value of 10 and get minus 2 along the way. So the value of being here is 8. If we back up one state again, we can see the value of being in this state is 6, because after a reward of minus 2, we'll end up in this state with 8. So that's the optimal value that you can actually get. This is V star in this MDP. It tells you how good it is to be in each of these states. And that tells you the most possible juice you can extract from this MDP. It doesn't yet tell you how to behave in it. To do that, there's two things you can do. Well, what we do is we basically define our Q stars now. In order to figure out what's the best action to take, we look at our action value function. So the action value function is now labeling these arcs with what's the value of each arc. So it's saying what's the optimal value of each arc. And so we know, for example, the optimal value of this arc here, that's 10. You're just going to take this, you're going to get your plus 10 reward, you'll be done. So that's the value of this arc here. The value of this arc here, we know that you're going to basically get minus 2 for taking that arc, and you're going to end up in a state that's going to get you 10 units of reward. So the value of this arc is 8, the value of this arc is 0. So now we can actually be able to make decisions. We can choose what's the optimal decision to take from here. Well, clearly you would pick 8 above 0, so you would choose to take this arc over here. Similarly, over here we didn't talk about the arc that goes down to the pub, and the value of this arc, and we'll see how to compute this in a minute, is actually 8.4. But once you've got this value, you can say, so this arc is basically averaging over all the things which might happen next, and looking at the value of 6, 8, and 10, and weighing them. And so now you can choose between, well, should I go into a state that gives me a reward of 10 units going onwards, or should I go to the pub, where I get this nice plus 1 reward now, and then still have a chance to get my 10? Well, you have to weigh them up, and it depends on the discount factor and all these other things. In this case, we see that this arc has a value of 10, this arc has a value of 8.4, so fortunately it turns out I'm not recommending that you all go and drink beer and you stay and listen to the course. Yeah, question?
There was a question earlier about infinite MDPs. You said it doesn't happen, but what happens then if you have a positive cycle? Say if pub was plus 100, would you keep going to the pub and studying for the rest of your life? Or?
So I was talking about a Markov chain at that point. Okay, so if you've got, there are technical conditions under which reasonably defined Markov decision processes are guaranteed to terminate. So if you want to find out more about that, there's a great book by Bert Sekas. He goes into all the technical conditions under which Markov decision processes are well defined. What we're going to talk about is largely the discounted case, because it's simpler. In the discounted case, you don't need to worry about any of that stuff. So if you do want to kind of remove discount factors and consider the case where you don't have discounting at all, then you need to consider what happens if you have infinite cycles and so forth. And there's two ways to deal with that. One of which is to look at all the technical conditions, make sure your MDP satisfies those technical conditions. The second case is basically to actually use the average reward version of reinforcement learning, which is in the extension to this class.
I think if you have a large enough reward on a certain edge in a positive cycle, you would even with a certain gamma, for example, if public plus 1,000,
Yes.
yeah, even though you've got your gamma, you might still go around and think.
Yeah, I should have added. So there were some technical conditions to my answer earlier, which were, with certain probability transitions. With the transition probabilities we had before, it wasn't possible to have infinite sequences. Of course, if you have a self cycle with probability 1, that does have an infinite cycle that can be drawn from that sample. So you have to have, if you want to deal with discounts of 1, there's machinery you need. Let's not worry about that. Things are much easier when we have discounting. Okay.
What name because he has a lot?
Yes, sorry. So it's in all his books, but so neurodynamic programming, it's there. But he has his new edition. Probably the best place to look is volume 2 of his new edition of his dynamic programming. Yes.
Optimal control, is it?
Yes, and I think it's volume 2 that has this in. Okay, so we've talked about optimal value function. That doesn't. So what we really care about, what's the thing we really care about? We care about the optimal policy. So the optimal policy, we need to understand what that really means. What's the best possible way to behave in an MDP? So we've talked about policies. A policy is just like a stochastic mapping, a mapping from states to actions that we take. And now we want to understand, what's the best one of these things? So far we've just talked about how much juice we can extract from the system, what's the maximum amount of reward we can get. We haven't yet talked about the policy itself. And so to understand what it means to be optimal, we need to define a notion of optimality. And to do that, we need to know what it means for one policy to be better than another policy. And so what we do is we actually define just a partial ordering over policies. So this partial ordering basically tells us, let's consider 2 policies, pi and pi prime. So these are 2 arbitrary policies. And we're just going to define this greater than or equal to operator. This is going to be some partial ordering over policy space. It basically tells us the intuitive thing, that one policy is better than another policy if the value function for that policy is greater than the value function for the other policy in all states. Okay? So greater than or equal to in both cases. So what this means is that it can't be worse, that it's not possible to say a policy is better than another policy if it's actually worse than that policy in one state. It has to be at least as good in all states for us to say that it's greater than or equal in the partial ordering. Okay, and then there's this very important theorem which you'll find in Patomo and all the important texts on MDPs. And this basically tells us that for any MDP at all, there is an optimal policy that is better than or equal to all other policies. So you should think about that. It's like, wow, okay, this is a good thing. You don't end up with this weird situation where, sometimes you need to think about taking this policy for a little bit of the MDP and this other policy for a little bit of the MDP, and that combination might be better. There's always one unique policy. There's always at least one optimal policy pi star, not necessarily unique, that is better than or equal to all other policies. So there is always an optimal policy. This pi star tells you one way to behave in your MDP that will extract the maximal juice from that MDP. And we've already seen that that's true from the Q star. Like if you have Q star and you pick the action that chooses the arc with the biggest Q star, that gives you one such policy. Okay? But the theorem basically tells you that that's true for any MDP, that this really is the best thing that you could find at the MDP. There's not going to be some other thing that's better, there's not like some weird averaging policy that's going to do better than this. Furthermore, it is possible to have more than one optimal policy. So it's possible that, for example, the simplest case is that imagine there's one action in your MDP where there's 2 separate actions that take you to the same state. It doesn't really matter which one of those you take, you're going to end up in the same state. They both can be optimal. It doesn't matter which one of those you choose, you're going to get the same optimal value out of this MDP, whether you go left or go right. Okay, so there can be more than one optimal policy, but if they are optimal, then all optimal policies they extract the same amount of reward from the system. They get the same amount of juice. So the value functions for those policies are the same. And specifically, the amount of value that they get can be given by the optimal value function, by the optimal action value function here. Okay, so the value of pi star is actually exactly the optimal value function that we defined earlier. So the V star and the Q star that we defined in the previous slides are precisely the numbers that you extract if you try to evaluate the optimal policy. So if you look at how good the optimal policy is, then it is indeed the maximum amount that we thought we could get out of the system. So this is like a sanity theorem, like that all the things you would hope to be true are true, and that everything is sane, and there is this thing called an optimal policy, and it does give you the maximum amount you can get from your MDP. Okay. So how do we find this thing? Well, we've already seen this intuitively, so this is just writing it down in equations. It's just saying that all we need is what you solve for Q star, and then you pick the action that gives you the most Q star. So in every state, what do you do? If you're in state S, well, you just pick the action A with probability 1 that maximizes Q star, and that is the action that will give you maximum possible reward. And there is always a deterministic optimal policy. So not only is there an optimal policy, but there's a deterministic optimal policy, and this gives you one such deterministic optimal policy. Okay. And the good thing about this is, once we've got Q star, we're done. The game is solved. We're happy. So let's do this one last time back at our student MDP. So now what we're going to look at is the optimal policy. So now what we're looking at is these arcs, remember, represent the actions that we can take. Like we can study, or we can go into Facebook, we can study, or we can go to the pub. And these red arcs now are highlighting the optimal action value. The optimal policy, pi star, is highlighted in red here. This is the undiscounted case again. So it's just this simple path all the way through our studying and studying and studying again that we'd already identified. But we can see that it must be the case again just by looking at the Q star values, which are also highlighted, and seeing that the optimal policy is always the one that picks, but whenever you've got two choices, it picks the one with the highest Q. So specifically, over here we've got the choice between Q star equals 10 for studying again, Q star equals 8.4 for going to the pub. So the optimal policy, the red arc, is the one that maximizes that and gets us the most reward going into the future. Okay, so how do we arrive at this Q star in practice? How do we actually arrive at figuring out these Q star values? These Q star values we've seen time and again, they're central. This is the central quantity we're trying to figure out so that we can just bang, pick the right action without even any look ahead or further thought. So once we have Q star, we're done. We've solved the MDP, but how do we arrive at Q star? So intuitively, what did we do? Well, we kind of worked our way backwards. We started off at this final state. We looked at the value of taking this arc, which was kind of trivially 10. You go to here, you finish, you get plus 10 along the way. And then we worked our way backwards, and we kind of did this look ahead with a one-step look ahead, where we started here and we said, okay, you start here, you look ahead one step, you end up with 10, work your way backwards. And that working backwards is precisely what we get out of a Bellman equation. So now what we're going to talk about is the Bellman optimality equation. So if you just open a textbook and hear about the Bellman equation for MDPs, they're talking about this one, not the one we looked at before. It's the Bellman optimality equation. This is the one that tells you how to really solve your MDP. The one that tells you, how do you relate the optimal value function to itself. So before we looked at the Bellman expectation equation for MDPs, which told us how V pi related to itself. So we looked at, for example, under this average behavior policy where you might go right or left with equal probability, how did the values relate to themselves? Now we're looking at really the optimal values. We're looking at the best things. We're looking at these, something like these red highlighted guys, like the values in these circles now, 6, 6, 8, 10. The maximum amount of juice you can get from your system, how does that number relate to itself? And what we can do is do like a one-step look ahead again. And so the way to understand this is, again, by this one-step look ahead, you can ask, well, what's the optimal value of being in some state? Well, you can consider each of the actions that you might take will take you to one of these chance nodes here, one of these action nodes. And we can say, when we reach that action, we can look at the action value. This is the red arc, the number on the red arc. We can say, this had a number on the red arc, which was 8, and this had a number on the red arc, which was 10, or whatever it was. And now, what we do is, instead of taking the average of these guys, we take the max over these guys. So we're basically saying, look at the value of each of the actions you can take, and pick the max of them. And that's going to tell you how good it is to be in this state here. It's simply the max of all the Q values. I can go left, I can go right, I look at how much reward I get in each case, and I pick the one that gives me the most. Okay? So the value function of a state is the max of the Q values of each of the actions you can take from that state. Okay. Now we're going to do the other half. So remember we had V going to Q, now we're going to do Q going to V. So now we want to know, well, how good is one of those red arcs in that diagram? How do we know what the optimal value is for being in a particular state and taking a particular action? How do we know that the study arc has a particular optimal value to it? Well, again, we can do a one-step look ahead, but now we're looking ahead over what the dynamics might do, what the environment might do to us, where the wind might blow us. We don't control this. This is like going to the pub and then, we don't know what will happen in the pub. It's a crazy place and we might end up in all these different situations. And each of those states that we end up in has some optimal value. And so we kind of, this is like an inductive argument. We sort of assume that we know inductively the optimal value of each of those states that we might end up in. And if we know the value of each of those states that we might end up in, we just need to average over them now. There's no max here. We don't get to pick where the wind blows us. We have to average over all the things the environment might do to us, and that tells us how good our action is. So our action is, the optimal action value is just the immediate reward plus the average over all the probability that the wind might blow us left, the probability the wind might blow us right, multiplied by the optimal value of being in that state. Okay? And again, what we can do is put those two pieces together. When you put those two pieces together, you have a recursive relationship that relates V star to itself. So this gives us an equation that we can solve. Okay? So this is now a two-step look ahead. We're looking ahead over the actions we can take here and maximizing over those. And we're also looking ahead over the dice that the environment might roll. And we don't maximize over the dice. We don't control the dice. Instead, we average over the dice that the environment can roll. And we do this two-step look ahead over our actions from this state and all the things the environment might do to us. And then we look at the optimal value of where we end up. We back these things all the way up, and that tells us how good it is to be in this state here. So that's the Bellman optimality equation of V star. Okay. So finally, just before we give one last example, we can do the same thing, flipping the diagram around and starting with the action values. And this is to arrive at a recursive relationship between the Q star values and themselves. So this isn't really saying anything different to the previous slide. It's just like a reordering of the same idea. And the reordering tells us that if we start and we want to know how good is one of these arcs, like how good is it to be in a particular state and take a particular action, now we first of all consider where the wind will blow us. We average over the dice which the environment's rolling, and wherever the dice roll, we get to make a decision. So wherever the wind blows us, we get to decide, pick one action after that, and we get to maximize over the decisions we take. So we average over the dice that we roll, and we maximize over the decisions we take, and for each of these leaves, we consider the action value, the optimal action value, like how good is it to be in this state taking this particular action, or in this state taking this action. We back that up all the way to the beginning, and that tells us the Q value of the root of this diagram. Okay. So let's make that concrete by picking one state in this diagram. Probably absolutely stick to the teeth of this student MDP by now. Anyway, I promise it won't come up too much again. So here we start off in this state. We consider we have two possible actions that we can take. So this one's rather straightforward. There's no noise that in the environment. We're not considering any dice rolls. It's just like people said before. Implicitly, there's like the environment always rolls the same way and takes us here. If we take this action, the environment always rolls the dice the same way to take us here. So we're just looking ahead one step by saying that the value of this state, 6, so this is V star of this state, 6, is equal to the max over all the things we can do here of the value function of where we end up. So we know that inductively, if we assume that these other values are correct, then we assume that this has an optimal value of 6, this has an optimal value of 8, and so if we maximize over all the things we can do, we see that oh yeah, there's a -2 along the way as well, that's why minus doesn't work. So you can either get -1 followed by ending up in a state with 6, so this has a value of 5. If we take this arc, so Q star of this arc is 5, or this way, we get -2 from our 8, and we get 6 So we choose to go this way, and our value function is 6. Okay. So how do we solve this in practice? So previously we saw that we had these Bellman equations with expectations that we could just solve by doing a matrix inversion. So that's very appealing for those of you who like MATLAB and these nice tools where you can just type in your matrix, type in your vector representing the rewards, and bam, do your matrix inversion, you're done. Unfortunately, that doesn't work for optimizing the Bellman optimality equation because we have these nonlinear equations now. We've got a max in addition to our expectation, and we want to solve for this equation that relates V star to itself or Q star to itself with a max over these expectations. So in general, there's no closed form to this thing, and we have to be smarter. And how do we be smarter? Well, using iterative solution methods, of which the best known examples are value iteration, policy iteration, which we'll talk about in the next class. These are dynamic programming methods for iteratively solving these recursive equations. And Q-learning, which we'll talk about in a subsequent lecture. And
The matrix solution itself is implicitly iterative underneath. You don't get away from doing any sort of iterative calculations. I mean, to solve that matrix equation, it's still an order n-cube problem where you have to iterate in some sense to get the solution.
Well, I mean, there's computation required to solve the matrix, and there's steps to that computation.
Right.
But it's not. So by iterative solution method, we mean something more like where you have an equation which you iteratively apply. At each step, you apply the next step of that update. So you start with some estimate, you update your estimate towards a new estimate, and so forth.
Right.
Now, of course, there are iterative approaches to matrix inversion, like the Sherman-Morrison trick, which can be applied to reinforcement learning as well. And so there are cases where the matrix inversion can be reduced in complexity from n cubed to n squared. Those are special cases, and so I'm talking about the general approach here. So yes and no. Okay, so we're just about out of time. I think I want to really just take questions and make sure people are following rather than going into the extensions in any great detail. So this is a great time if you feel that something was unclear, and now's your chance to ask. Otherwise, I'm just going to assume that that's all the notes were incredibly perfectly clear and everyone understood everything, which I'm very confident is not true. Yes, please.
So if you have an imperfect model or have missing information, how would that translate to your diagram of the MDP? Would you have missing nodes, or would you have a uniform distribution where you should have a different one, or would environment guys would?
Okay, so it's a great question. So the question is, in reality, the MDP is just a model. We're trying to model some real phenomenon out in the world, some real environment. How do we represent the fact that our model is imperfect? We're actually going to have a class on where we'll talk about model-based reinforcement learning. If there's time, I'll talk about some of the approaches to uncertainty. So some of the classical approaches to uncertainty include explicitly representing the uncertainty in the MDP. So you could be Bayesian, for example, have some posterior estimate of what the MDP dynamics are, and then solve not just for one single MDP, but for a whole distribution over MDPs, and find the policy that's optimal with respect to all of them. That's computationally very difficult. Another approach is to actually factor in the uncertainty in your representation of what's going on in the world into your MDP itself. So you'll say you're in a state where not only am I in a state where my robot's here, but I'm in a state where my robot's here and I think that the world has these dynamics, or I'm in a state where the robot's here and I've seen these observations so far which implicitly tell me something about the uncertainty of what's going on in the MDP. So that can be much more tractable. You don't necessarily need to explicitly reason about all the uncertainty in the environment, but it's maybe a little less intuitive to understand the form of the uncertainty. The uncertainty isn't made explicit. And then maybe the only other thing to say, which we already touched on, is that sometimes it's sufficient to just say, well, accept that that our model is imperfect, and use a discount factor to capture the fact that we've got some uncertainty. You can also make the discount factor variable to represent the fact that you're more uncertain in some states than others. So you don't have to have 0.9 everywhere. You could have 0.9 in one state, 0.99 in another state, representing how bad your model is in that situation. So it's a very active research area. I think it's a great question. Yeah.
So everything you've shown us today seems to be sort of geared towards like maximizing reward.
Mm-hmm.
But is there anything implicit in there that would also like have a consideration of risk? So like if you might be interested in maximizing your reward at a future time and choosing that policy, but there might be some chance that choosing that policy, that there's also an increased risk.
Okay, so the question is, everything's just talking about maximizing reward and expectations of those reward without explicitly considering risk or variance of those returns. So I think the correct answer to that is to say that you can always transform any MDP with no risk into, so if there's some amount that you care about your risk, like let's say that there's a cost that depends on the variance of your returns, there is another MDP which has a different reward function that already factors in the variance of those rewards into the actual reward that you see at the end of your trajectory.
So that can be implicit in this model you've shown us today, basically.
So there is a transformation of any risk-sensitive MDP into another MDP. However, that transformation can be quite complex. So you might need to remember all the things that you've seen so far, and it can be a more complicated MDP that you end up having to solve. So that's the first answer. The second answer is to say that a bunch of people do specifically consider risk-sensitive MDPs, where you don't just consider expectations, but you consider what's the variance of those rewards at the end of the day. So there's a bunch of work out there, and I'm happy to give you pointers to that if you're interested. Any other questions? Okay, one more, and then I just want to say a couple of words before everyone piles out. Oh yeah, sorry, this guy was actually waiting for longer.
Some example for intuition for the Bellman equation, for instance. I mean, obviously you have two parts which balance, and I think it's just pure mass. I mean, there are situations, for instance, in finance where somebody would actually balance it, in terms of arbitrage, but in terms of like real equation, real situations like a robot or like a Atari game, what does it make it sort of to actually hold true?
Okay, so the question is, what's the intuition behind the Bellman equation in some real example? So if we take the Atari game as an example, so the Bellman optimality equation, let's focus on that one. That's the crux of where we got to. The Q star or V star is telling you, what's the maximum amount of score you can get. You're in this screen here. What's the maximum score you can get from this screen here? And the intuition is that all you need to do to get that maximum score, this is called the principle of optimality. So the principle of optimality tells you that the way to get the maximum score is to behave optimally for one step, and then to behave optimally for the remainder of your trajectory. Okay? If you behave optimally for the remainder of your trajectory, that's the value function from the state that you end up in. And so now all you need to do is to figure out, well, how do I behave optimally for one step? And the way that you behave optimally for one step is to maximize over those optimal value functions in the places you might end up in. So it's like you might move Pac-Man to the left, and you might move Pac-Man to the right. If you move Pac-Man to the right, and you can get 100 points of optimal value from that point onwards. Or so moving to the right, you might get plus 10, and then 100 points of optimal value afterwards. Moving to the left, you might get plus 20, but then only 50 points of optimal value afterwards. And so the intuition is that just by breaking down your trajectory into these two parts, into the optimal decision at one step and the optimal decision from there onwards, you can describe what it means to have optimal dynamics for the whole problem. Okay. One more question, then I just want to say a couple of words about the extensions, but without any details at all, so don't get scared. Yes?
In terms of practical applications, say you have 1 million states and 1 million actions per state, how do you arrive at the rewards?
So if you have 1 million states and 1 million actions per state, you have a large MDP, and so now you're asking how do you actually solve the MDP to find the optimal value function? Is that the question? Was the question how do you solve it, or how do you decide on the immediate rewards?
How do you model the rewards? Probably not manually typing everything.
I see. So the question isn't how do you solve the MDP; it's how do you model the MDP? How do you represent a large MDP? So typically the reward function is given by the environment dynamics. So it's given by so for example it might be imagine you're playing Atari. The score that you get, there are many more than 1 million states in Atari. And yet, the score is just a function of that state that you're in. So it's something which, you're in this state, you query the emulator, you say, what's the score, or you extract the score from the screen, and it's just a function that depends on your state. So typically there's some function mapping state to reward, and that function characterizes imagine you're a programmer and you're trying to tell your program what the problem is you're trying to solve. The reward function is kind of like the definition of the program. You're asking the program to solve this particular problem. It's part of the problem definition. So the reward is just a function it's part of the environment. It's part of the thing describing how the environment state gets mapped into reward. So in any reasonable problem, you'll see that there's a way to transform this and describe the reward, normally quite conveniently. There's a big open question, which is how do you best model the reward in the way that actually leads to intuitively what we as humans think of as the best solution. Okay, very briefly, I just wanted to put up this slide just to highlight that there are some additional slides, extensions to MDPs. This is not examinable material. I do not expect you guys to go off and revise stuff which I haven't told you about. And in general for these classes, I'll try to make it very clear what's non-examinable material. And if we run out of time at any point, don't panic. You won't suddenly find a question that crop up in the exam which we didn't cover. But the extensions are on the slides just there as additional material, in particular telling you how to deal with infinite MDPs, continuous MDPs, partially observable MDPs, undiscounted average reward MDPs. These are the major extensions to the MDP framework. Just to give you some sense, I think just out of interest you can get some sense. It's not details, it's just a brief outline showing you how you can move beyond this to the case where you're trying to control some real aeroplane or helicopter with continuous actions and perhaps even continuous time steps, or where the state that you see doesn't tell you everything about the environment, but you just get to see the robot's camera at every given time step, and you don't get exposed to the Markov state that's actually inside the environment. You just get to see what your agent sees at that moment. And finally, the case where we can deal with undiscounted case by basically looking at a limiting case where we average over, where we look at the average reward going into the future, the average reward per time step, instead of the discounted sum of rewards. It's a different definition of return that actually works out very neatly. So just if you're feeling enthusiastic, go and have a look. There's pointers to elsewhere. And otherwise, the remainder is next week we'll start to talk about how to solve these things. So this is just defining the problem. Next week